Hello everyone, my research topic is the driverless detection technologies for Android application, and my contents include those parts. I directly go to the first one, introduction. So, currently, driver fatigue is one of the main causes of road accidents. According to the data from the National Highway Traffic Safety Administration of the United States, almost 2.5% of road accident fatalities can be attributed to driverless driving. So actually, I have personally experienced this firsthand. Last week, when I was driving on the highway in China, I fell asleep at the wheel. So unfortunately, when I woke up, my car had already collided with the roadside barrier. Fortunately, I didn't get any hurt. So it reminds me that currently most fatigue detection systems are only available in the new and high-end vehicle mode, which like my car, the older one, lack such features. So based on this experience, I'd like to develop a easy use, high performance, lightweight, user-friendly real-time drive fatigue detection system. The system will based on single-shoot multibox detector and deep learning modes. And importantly, I am planning to integrate it into Android devices to achieve a high accuracy in fatigue detection, which means with any Android devices with camera, you can have your own fatigue detection system. Literature review. In this part, we will review some exciting technologies for fatigue classification. So the first, recently, research has explored innovative approaches to detect driver fatigue, such as McDonald's proposed an algorithm utilizing parameters like steering wheel angle, vehicle speed, and acceleration inputted into a bias network to discern drowsiness signal with a lower false alarm rate than traditional methods like PERCLOS, based on yield movement and pattern prediction of fatigue. Also, additionally, VAIT investigate non-recurring EEG brain-computer interface, finding them more variable but less effective compared to forehand EEGs, suggesting potential development of less invasive and more comfortable fatigue detection handbands. Furthermore, some companies are attempting to integrate different technologies, such as combining eye features analyze, physiological parameters monitoring, and image recognition using multiple sense data to enhance the accuracy and reliability of fatigue detection. However, all of those integrated technologies require a large number of sensors and proprietary solutions, resulting in higher costs. Our proposed approach, on the other hand, offers the advantage of achieving the same detection effectiveness with fewer devices and lower costs, as well as being easy to install and deploy. Problem statement. So currently, the fatigue driving still remains one of the main factors contributing to the traffic accident. And many currently fatigue detection technologies relies on intrusive sensors or lack sufficient accuracy and immediacy, making them challenging to deploy widely in practical applications. Therefore, developing a non-intrusive, efficient, and accurate fatigue detection system is particularly crucial, and the current deficiency in automatic fatigue detection include the immaturity of technology's low detection accuracy, poor immediacy, and most important, a lack of easy to deploy research arm and objectives. So our research arm is to develop and validate a lightweight, efficient, and high-performing driverless detection system that leverage single-shoot multibox detector and faster landmark detection technologies. This system is designed to be integrated into Android devices, providing real-time detection of driving behavior to enhance road safety. And to reach our research arm, I divided it into three small research objectives, the three key aspects. First one, precisely identifying human faces to provide a base for fatigue detection, and the second one, training and validating the deep learning mode SSD for accurate determination of fatigue states in detected phase, and the last one, integrating the trained SSD mode into Android software, enabling its easy invocation through an app. And at the same time, we needed to guarantee the high performing and lightweight and efficiency methodology is the methodology Firstly, I will adopt the positivism approach in research methodology, utilizing the deductive approach along with observation and empirical validation to design our research method and technology, which means that we will validate the reliability and stability of our system through experimental method. Specifically, I want to focus on the quantitative method to focus on two key components. The first, verify the effectiveness and stability of our SSD mode, and the second, assess the effectiveness of detection system on Android devices. I will give an explanation later. At the same time, I divide my research system in four different parts. The first part is real time face detection, and the rest of the part I will give an explanation later. So let us directly go to the first part, real-time face detection. So let us start from the real-time face detection. Utilize the OpenCV library for real-time image capture and employ the Hierarchical cascade method for face detection, followed by resizing the images to fix the size of 224 times 224 pixels to ensure consistency in input data for neural network modes. The driver draftiness dataset DDD contains over 10,000 facial images of drivers extracted from videos and annotated with bounding box indicating drowsy and undrowsy state. We could see here. So it is divided into a training set. It contains 10,000 samples and a test set 500 samples. It's very suitable for training deep learning objective detection models. 1. The SSD mode. The single short multi-box detector SSD is based on CNN mode. Actually, it's an efficient object detection mode known for its single pass prediction of bounding books and categories, enabling real-time applications. It utilizes multi-scale feature maps, default boxes, and end-to-end training, eliminating the need for separate region proposal and classification steps, while employing non-maximal separation during inference for accurate object detection. So, the SSD mode can effectively detect and classify the drowsiness states of driver images through training and inference processes, determine fatigue or non-fatigue state by predicting bounding box and category probabilities. Need to evaluate the trend SSD mode using a testing dataset. So computer metrics such as accuracy, recall, and FE score to assess mode performance. Also, we needed to generate a confusing metrics to visualize the model's classification performance across two different categories. Also, we needed to result analyze the model accuracy, recall, and FE score. Also, the confusion metrics to identify potential misclassification across different categories. And based on our results, we needed to do adjustment and improvement, explore technologies such as data augmentation, model architecture adjustments, or parameter tuning for enhancement. Okay, the next part is deploying an SS detection model on Android device. We will use three technologies for this function. The first one is ONNX mode. ONNX is an open ecosystem that allows AI developers to move mode between different frameworks, tools, runtimes, and computers. In short, ONNX provides a common format for machine learning models. This means that you can train a model, for example, in PyTorch, and then convert it to ONNX format, thus allowing for inference on any platform that supports ONNX. So in first step, we need to convert our SSD mode to ONNX mode. That second one is TNN mode. TNN is a lightweight neural network inference engine open sourced by Tencent U Lab, designed specifically for high performance edge computing on mobile devices. So TNN is optimized for low memory and computation power requirements, making it suitable for running on resource-constrained mobile and embedded devices. So in that step, we need to convert our ONNX model into TNN model. To realize this function, we needed to use this tool. The ONNX to TNN tools is one of the most crucial mode conversion utilities in TNN. Its primary function is to convert mode from the ONNX format into TNN format. So with these three technologies, we could deploy TNN mode on Android devices. It involves integrating the TNN library into the Android project and using TNN APIs to load the converted mode, processing input data and to be compatible with the TNN engine, executing inference within application to obtain results. The last step, we need processing the results into a user understandable form, such as classification labels and detection books. Here is the Photoshop to demonstrate how to convert our SSD mode to ONX mode and TNN mode, and finally to deploy TNN on Android devices. Okay. It's the expectations. We have several expectations of our detection system. First one, real-time performance. The SSD mode should ensure efficient real-time performance when running on Android devices with an ideal frame rate at least 30 FPS to ensure timely detection and response to the driver fatigue state, minimize the impact of delays on driver safety. Accuracy. The mode accuracy in detecting driver fatigue should reach at least 90% to reduce false alarms and misdetections. This means the model can accurately identify key indicators of fatigue driving and low power consumption. The model deployed on Android device should have a low power consumption, not excessively draining the device battery. Ensure monitoring for extended period without interruption due to the battery condition, and user-friendly. The application interface should be simple, clear, display the detection results to driver and issuing warning when signs of fatigue driving and detected, promoting the driver to take appropriate actions such as resulting or switching drivers. And also we need adaptability and stability. Also the privacy protection ensures that the application operated handles and protect the user privacy information during driver fatigue detection. The last part is project management. Due to the time constraint, I cannot expand it very detailed. So basically, in the first stage we needed to do the project initiation and planning, such as we need to make sure our project objectives and project scope. We needed to make sure our project team and stakeholders, such as the developers and the users, and we needed to do the work breakdown structures. We to use the work breakdown structures to divide our projects into multiple phases and tasks. And the last stage about the timeline. If we project start on 5th May, and then maybe we will take about 12 half months to do the system design and half months to development and another 20 days for testing and improvement, and then we deployment and delivery to our customer, and we get some feedback and to do some improvement. And the last decision will be the paper report writing. So it's all basic as a basic timeline. We will adjust it by the real situation. And the last part we need to do the project execution and control. If we have more than 2 or 3 developers or end use, we needed to use some team collaboration management methods and tools. So such as this is tool to facilitate team collaboration and task tracking. And we also need to have the risk management and communication method and identify the potential risks in advance and develop risk response structures. Also, we need to develop a communication plan to ensure project updates are promptly conveyed to all relative parties, such as other developers or the users. So that's all my presentations.